Tonight, the universe stops feeling like a backdrop and starts feeling truly enormous. Galaxies are only the beginning. Beyond them lie distances so vast that light itself struggles to cross them, and within them are layers of reality that make Earth feel almost impossibly small. This is the real scale of the cosmos, from the edge of the observable universe to the tiny place humanity calls home. If this kind of deep space journey is worth exploring, please like the video, subscribe to the channel, and settle in, for the real scale of the universe will blow your mind. At the widest scale that astronomy can describe, the universe appears as a sphere of visibility centered on the point from which it is observed. This is not because Earth holds a special place, and not because the cosmos is arranged around one world, but because light takes time to travel. The observable universe is the portion from which light, or other detectable signals moving at the cosmic speed limit, has had enough time to arrive since the beginning of cosmic expansion. Beyond that limit, space may continue for an unknown distance. Observations show only the part that has been able to send information across time. Everything in this first region begins with that boundary of visibility, a horizon made not of walls or matter, but of time, distance, and the changing fabric of space itself. The age of the universe is about 13.8 billion years. At first glance, that number seems to set a simple radius for the farthest visible edge. Light that travels for 13.8 billion years might appear to define a sphere with a radius of 13.8 billion light years. The actual scale is much larger because space expands while light is in motion. As the light travels, the distance between regions of space grows. For that reason, the most distant matter now seen in ancient light lies much farther away in present distance than the travel time alone would suggest. The observable radius is estimated at about 46 billion light years, making the full observable diameter about 93 billion light years. These figures describe the present scale of the visible cosmos, not the distance when the light first began its journey. This outermost region is not seen as it exists now in a simple, single moment. Looking far away also means looking far back in time. Nearby objects appear in relatively recent states because their light reaches Earth quickly. Distant galaxies appear as they were millions or billions of years ago. The most distant visible glow comes from a time when the universe is very young, long before stars and galaxies take the forms now familiar in deep sky images. Distance becomes a record of history. The farther the view extends, the earlier the scene becomes. In this way, the observable universe is not only a vast region of space but also a layered archive of cosmic time. The oldest light that can be seen directly with ordinary electromagnetic observation is the cosmic microwave background. This faint radiation fills the sky in every direction. It comes from a time about 380,000 years after the beginning of cosmic expansion, when the early universe cools enough for electrons and atomic nuclei to combine into neutral atoms. Before that moment, the cosmos remains a hot plasma, meaning a state of matter in which charged particles move freely and scatter light constantly. In that earlier state, space is opaque. After neutral atoms form, light travels much more freely. The cosmic microwave background is the afterglow from that transition. It does not mark the beginning of everything, but it does mark the earliest surface from which light can move across space without being trapped again and again by charged matter. Seen today, that ancient glow has been stretched by expansion into microwave wavelengths. It appears almost uniform, with tiny variations in temperature from place to place. Those slight differences matter deeply. They show that the early universe is not perfectly smooth. Small differences in density are already present. over immense spans of time, gravity acts on those differences and helps shape the larger structures that later emerge, even at the greatest visible scale. The universe carries traces of unevenness. The wide horizon is not blank. It contains subtle patterns that reveal how matter begins to gather. Expansion itself is central to the meaning of scale. Galaxies are not simply flying through a fixed emptiness in the way sparks might move through air. On the largest scales, space between distant regions increases. This observation first becomes clear through the study of galactic redshift, the stretching of light toward longer wavelengths. In general, the farther a galaxy lies, the faster it appears to recede. This pattern is described by the expansion of the universe. It does not mean that every galaxy moves away from one special center in ordinary three-dimensional space. Instead, every large region sees distant regions receding, because the whole fabric of space expands. The observable horizon is therefore dynamic. It is shaped by the history of expansion, by the changing rate at which space grows, and by the finite speed at which information can travel. Modern cosmology describes this large-scale behavior with a model in which ordinary matter, dark matter, and dark energy all influence the history of expansion. Ordinary matter is the material of stars, gas, dust, planets, and living things. Dark matter is a form of matter inferred from gravity, not seen directly in light. Dark energy is the name given to the cause of the observed accelerated expansion of the universe. Observations indicate that ordinary matter forms only a small part of the total cosmic energy content. Most of the cosmos is made of components that are not directly visible in the usual sense. Even at the broadest possible view, much of reality remains known through indirect evidence rather than direct sight. The geometry of the observable universe appears close to flat on large scales. In simple terms, flat here means that space, across the widest measurable distances, does not show strong overall curvature in the way the surface of a sphere does. Measurements of the cosmic microwave background, galaxy distribution, and other large-scale signals support this picture within present uncertainty. It remains uncertain whether the entire universe beyond the observable region is exactly infinite, extremely large but finite, or shaped in some broader way that current observation cannot yet determine. The visible horizon sets a limit on evidence. Beyond it, scientific language becomes more careful. Observations indicate what can be measured within reach. Outside that reach, the full extent of space remains unknown. Within this outer region, light from the earliest visible epoch and light from younger galaxies both arrive together at the present moment, each carrying a different age of the cosmos. The sky becomes a map made from many times at once. No single image can show the whole in a human sense. Even the best deep field observations cover tiny patches compared with the full sky. Yet from those narrow windows, from the ancient microwave background, from redshift surveys, and from the careful measurement of distance and motion, astronomy reconstructs a coherent picture of enormous scale. The observable universe emerges not as a solid shell, but as a measurable domain with a real edge of visibility and an unknown continuation beyond it. In this widest region, scale no longer feels like an extension of landscape. It becomes a relation between time, light, motion, and the growth of space. The outer limit is not reached by travel in any ordinary sense. It is reached by perception and inference. Matter at the farthest visible distances sends signals from the deep past, and those signals cross an expanding cosmos before arriving at a planet around one star in one galaxy. From that arrival, a boundary is drawn. It is the largest region science can presently describe through direct observation, immense beyond familiar thought, yet still only a portion of the whole that may exist. Beyond the broad horizon of visibility, the largest visible pattern within the universe is not a uniform fog of matter, but a textured arrangement of strands and gaps. On the greatest scales that galaxy surveys can map, matter gathers into an immense network often called the cosmic web. A web in this sense is a connected pattern of long filaments, dense knots, and broad empty regions. The word is a simple description rather than a literal structure. No threads are woven by hand, and no fibers stretch through space. Instead, gravity shapes matter over billions of years into a pattern that resembles a network when viewed across vast distances. In this region, the main impression is one of delicate organization spread across extraordinary emptiness. The cosmic web forms from small differences in density present in the early universe, after the release of the cosmic microwave background. Matter is no longer trapped in hot plasma in the same way, and gravity begins to amplify the unevenness that already exists. Regions with slightly more matter exert slightly more gravitational pull. Over time, they attract additional material. Regions with slightly less matter lose relative ground. This process unfolds very slowly by human standards and over enormous spans of space. It does not produce a random scattering of galaxies. It builds a large-scale pattern in which matter tends to stream toward denser regions, leaving other regions increasingly sparse. Dark matter plays a central role in this structure. It cannot be seen directly through emitted light, but its gravity shapes the formation of galaxies and clusters. In current cosmology, dark matter begins gathering into broad halos and filamentary patterns before ordinary gas settles into the same gravitational landscape. Gas falls into these deepening wells, heats, cools, and eventually forms stars and galaxies in the denser parts of the network. The visible universe therefore traces an underlying scaffold that is mostly unseen. What telescopes record in starlight is only part of the total structure. The shining galaxies are the bright outlines of a much larger gravitational pattern. When large galaxy surveys measure the positions of millions of galaxies, they reveal this network in striking form. Galaxies are not spread evenly like grains of dust in still air. They line the edges of enormous voids and concentrate where filaments meet. Some filaments stretch for hundreds of millions of light years. Along them, galaxy groups and clusters appear like beads on long, luminous strands. Between them lie vast regions with very few galaxies at all. These emptier spaces are not perfectly empty, but compared with the crowded filaments they contain remarkably little matter. The contrast between concentration and absence gives the cosmic web its character. The web is not a rigid frame suspended in still space. It evolves as the universe expands. Filaments grow more pronounced as gravity pulls matter inward, while the general expansion of the cosmos carries distant large-scale regions farther apart. Within this expanding environment, local gravity gathers material into denser structures. The two processes happen together. Space grows on the largest scales, while matter within the web flows toward nodes and strands under gravitational attraction. The result is a universe that becomes more structured over time in some places, even as the overall distances between major regions increase. At the intersections of the filaments, matter becomes especially concentrated. These junctions are the sites where galaxy clusters and larger associations build up. Along the filaments themselves, galaxies and gas continue to move, often falling inward toward denser knots. Some of the gas between galaxies is very thin and difficult to detect. but observations indicate that a significant part of ordinary matter exists in diffuse intergalactic form, spread through filaments and surrounding regions. Much of it is heated to high temperatures by gravitational collapse and shock waves, making it faint and challenging to study. For many years, astronomers recognized that some ordinary matter predicted by cosmology seems difficult to account for directly. Increasingly sensitive observations suggest that a notable fraction of it resides in these large-scale, thinly spread structures between galaxies. The scale of the cosmic web resists ordinary comparison. Mountain ranges, river systems, and weather patterns may offer rough visual analogies, but the web exists across distances so large that light itself needs millions of years simply to move from one part of a filament to another. A single galaxy, which already contains vast numbers of stars, becomes only a tiny point within this broader pattern. Even galaxy clusters, among the largest bound structures in the universe, appear as local condensations within a still larger network. The web is the arrangement into which such structures fit. It is not made of individual stars or planets in any direct visible sense. It is made of the distribution of matter on scales where whole galaxies serve as markers. Computer simulations help reveal how this structure grows. Starting from the small density variations measured in the early universe and applying the laws of gravity and cosmic expansion, simulations produce a filamentary pattern very similar to what galaxy surveys observe. Matter streams along preferred paths, sheets collapse into strands, and dense nodes form at intersections. This agreement between simulation and observation strengthens confidence in the broad cosmological model. It does not mean every detail is complete or settled. It remains uncertain exactly how all small-scale baryonic processes, meaning the behavior of ordinary matter such as gas, stars, and black hole feedback, interact with the dark matter scaffold across every environment. Even so, the large pattern itself is well supported. The web also carries a history of motion. Galaxies are not placed on filaments as static lights pinned to a dark ceiling. They form, move, interact, and sometimes merge within this environment. Gas can be stripped, heated, or compressed. Clusters can grow by drawing in smaller groups along the filaments. The emptier voids, meanwhile, become more strongly underdense as matter continues to migrate outward toward denser boundaries. In this way, the web becomes more contrasted with time. The rich regions gather more mass, and the poor regions become poorer still in relative terms. Although the cosmic web seems intricate, it arises from simple physical principles acting for immense periods: slight primordial unevenness, gravitational amplification, the influence of dark matter, the cooling and collapse of gas, and the continuous expansion of space together produce a pattern of remarkable scale. It is not designed, and it has no central intention. Its form emerges from the long unfolding of cosmic history, observations from telescopes on Earth and in space, together with redshift mapping and gravitational analysis, show that the universe on the largest scales is neither chaotic nor neatly uniform. It has a recognizable architecture. Within this region, the mind begins to leave behind the idea that the cosmos is simply a collection of isolated galaxies floating separately in darkness. Instead, galaxies belong to a connected landscape. They occupy strands, walls, and nodes within a network stretched across the observable cosmos. Between those strands lie gulfs so large and sparse that their emptiness becomes part of the structure itself. The real scale of the universe, at this level, is not only a matter of size, it is also a matter of pattern. Matter traces a web across distances so immense that even the brightest galaxies serve only as tiny signposts along a far greater design shaped by gravity and time. Within the cosmic web, some regions gather into broad complexes of filaments and clusters, while others remain strikingly empty across immense spans. These two conditions, concentration and absence, give the large-scale universe much of its visible character. In this region, attention rests on superclusters and voids, which are among the most extensive patterns that can be described before moving inward to smaller gravitational systems. A supercluster is a large association of galaxy clusters, galaxy groups, and connecting filaments that occupy the same general region of space. A void is a vast underdense region containing far fewer galaxies than average. Together they show that the universe is structured not only by what is present, but also by what is missing. A supercluster is not always a single bound object in the way a planet is bound to a star, or a star cluster is bound by its own gravity. Some parts of a supercluster may be moving toward one another under mutual attraction, while other parts take part mainly in the general expansion of the universe. The term describes a large-scale arrangement rather than a sharply enclosed body. These enormous associations can extend across hundreds of millions of light years. They include multiple galaxy clusters, smaller groups, long filaments of galaxies, and clouds of hot intergalactic gas. In deep surveys, they appear as broad provinces of higher density within the cosmic web. One of the most studied regions of this kind includes the supercluster environment around the Milky Way. Modern mapping of galaxy motions suggests that the local group, which contains the Milky Way and Andromeda, belongs to a larger flow pattern within a region called Laniakea. This name refers to a vast domain defined partly by the way galaxies move under gravity toward denser centers. It is not a simple solid object with a sharp physical wall. Rather, it is a mapped basin of motion within the larger network. Such descriptions show how difficult it can be to name and define the largest patterns. Different methods can emphasize position, density, or motion, and the exact borders of these great regions remain less precise than the borders of smaller bound systems. The matter within supercluster regions is arranged unevenly. Galaxy clusters appear as dense knots. Groups of galaxies lie between them. Filaments stretch from one concentration to another, guiding matter along preferred paths shaped by gravity. Much of the space, even inside a supercluster, is still thinly filled compared with the interiors of galaxies. These regions are large because they organize many separate systems across broad volumes, not because every part is crowded. The eye, when shown a map of such a region, notices strings, walls, and concentrations with dark intervals between them. The structure resembles weather fronts on a map only in the broadest visual sense. Its true dimensions are far beyond anything in planetary experience. On the other side of this pattern lie the cosmic voids. A void is not absolute emptiness. It may contain isolated galaxies, faint gas, dark matter, and a low background of radiation. Yet compared with the average density of the universe, a void is markedly depleted. Some voids are tens of millions of light-years across, and some are much larger. Their existence is a natural consequence of gravitational growth in an expanding universe. As matter slowly flows toward denser filaments and nodes, underdense regions lose relative material and become more empty with time. In this process, the cosmic web sharpens. Dense regions gather more matter, and voids become more pronounced. The emptiness of a void has physical consequences. Galaxies inside voids tend to be fewer and more isolated than galaxies in richer environments. Their histories can differ because they experience fewer close encounters and fewer strong gravitational disturbances from neighbors. Observations indicate that environment influences how galaxies grow, form stars, and interact with surrounding gas. Even so, the effect is not simple or identical in every case. Some galaxies in voids continue quiet star formation, while galaxies in dense regions may be shaped by mergers, stripping, and the hot gas of cluster environments. The main point at this scale is that emptiness is not passive background. It is an active part of cosmic structure, helping define the paths along which matter gathers elsewhere. Voids also help astronomers test cosmological models, because they are sensitive to the growth of structure and the expansion history of the universe. Their sizes, shapes, and distributions offer clues about dark matter, dark energy, and the behavior of gravity on large scales. Measuring voids is difficult because their boundaries are statistical rather than solid. A void is recognized through the scarcity of galaxies in a region, not through a visible edge. Different surveys and analysis methods can produce somewhat different catalogues of voids. Still, the general picture is robust. Large underdense regions are a real and widespread feature of the observed universe. Superclusters and voids together give the large-scale cosmos a grain. They prevent it from being featureless, yet they do not overturn the broader principle that, on the very largest scales, the universe appears statistically homogeneous. This means that when averaged over sufficiently immense volumes, matter distribution becomes more uniform. Locally and regionally, the texture is dramatic. Over still greater distances, the highs and lows average out. This distinction matters. The universe contains vast structures, but evidence does not show an endless hierarchy of ever larger bound objects without limit. There is a scale beyond which the cosmos smooths statistically, even though superclusters and voids dominate the view at somewhat smaller large scales. The names given to large structures often carry a sense of solidity that the physical systems themselves do not fully possess. A galaxy cluster is usually a more clearly bound object than a supercluster. A void is more a region of low density than a container with firm walls. These distinctions are important because the language of ordinary geography can mislead. Continents, oceans, and valleys on Earth have familiar boundaries linked to visible surfaces in the universe. Boundaries at this scale are often inferred from position, density, redshift, and motion. They are scientific descriptions of pattern rather than visible borders in space. Even so, the reality they describe is substantial. The Milky Way does not sit alone in a random sea. It lies within a structured environment made of neighboring groups, clusters farther away, filaments threading across space, and large underdense cavities beside them. Across the observable universe, countless galaxies participate in similar arrangements. Some inhabit rich supercluster regions where the number of nearby systems rises sharply. Others stand on the sparse edges of great voids, with fewer companions across startling distances. The contrast between these conditions shows the depth of cosmic unevenness that gravity has produced over billions of years. At this level, the scale of the universe becomes a matter of regional geography without ground. Great concentrations extend across hundreds of millions of light years, yet remain only districts within the larger web. Great voids open beside them, immense in size and thin in content, yet still crossed by faint matter and radiation. Presence and absence shape one another. Superclusters stand out because voids surround them. Voids are defined because matter has retreated toward filaments and knots. This balance between gathered structure and spacious depletion gives the large-scale cosmos a calm, sparse architecture, one that feels almost empty at first glance, and then, with slower attention, reveals an order spread across distances too large for instinct to hold at once. Within the broad provinces of superclusters, some regions become dense enough that gravity binds them into more definite systems. These are galaxy clusters, among the largest gravitationally bound structures in the universe. A galaxy cluster is a collection of hundreds to thousands of galaxies held together by gravity, along with enormous quantities of hot gas and a much larger reservoir of dark matter. In this region, the scale of the cosmos begins to feel less like a loose map of patterns and more like a deep well where matter gathers, circulates, and settles into a shared gravitational environment. A cluster is not merely a place where many galaxies happen to lie in the same direction. It is a physical system with mass, motion, temperature, and internal structure. At first glance, a galaxy cluster might seem to be defined mainly by its galaxies, bright elliptical galaxies, spirals, and smaller companions can indeed be seen spread through the cluster, each containing its own stars, dust, and planetary systems. Yet the visible galaxies account for only a portion of the total matter. A large share of the ordinary matter in a cluster exists not inside stars but in diffuse gas filling the space between galaxies. This gas is heated to extreme temperatures by the gravitational energy released as matter falls inward. At such temperatures, it emits strongly in X-rays rather than visible light. Modern observations show that a cluster is, in many ways, less a swarm of galaxies in empty space than a vast atmosphere of very hot gas in which galaxies are suspended. This intracluster medium, meaning the gas that lies between the galaxies of the cluster, can reach temperatures of tens of millions of degrees Celsius. At those temperatures, atoms are stripped of many of their electrons, and the gas becomes a plasma. The pressure of this plasma helps trace the depth of the gravitational well in which it sits. Because the gas is spread across enormous distances, it contains a tremendous amount of mass even though its density is very low by earthly standards. Observations in X-rays reveal glowing cluster cores, uneven flows, shock fronts, and signs of past mergers. The cluster is not a still arrangement. It is a living gravitational environment in which galaxies move at high speeds, while hot gas responds to collisions and compression on scales far larger than any single galaxy. Dark matter dominates the mass of most galaxy clusters. It cannot be seen directly, but its presence is inferred from several lines of evidence. The speeds of galaxies moving within clusters are often too high to be explained by the visible matter alone. The temperature and confinement of the hot gas also indicate much more gravity than stars and gas can provide by themselves. Another important clue comes from gravitational lensing, the bending of light by mass. When a cluster lies between Earth and more distant galaxies, its gravity can distort the background light into arcs, stretched shapes, or multiple images. By measuring these distortions, astronomers map the distribution of mass, including the invisible component. These studies show that the cluster is surrounded and permeated by dark matter, which forms the main gravitational framework of the system. Clusters grow over time through mergers and accretion. Accretion is the gradual gathering of matter by gravity. Smaller groups of galaxies fall inward along filaments of the cosmic web, bringing galaxies, gas, and dark matter into the cluster. Sometimes two clusters or large subclusters collide. These events release enormous energy and can reshape the internal structure of the system. The galaxies themselves usually pass one another without direct collision because the space between stars is so large, but the gas clouds associated with the clusters can collide and slow down. This separation between ordinary gas and dark matter during mergers has provided especially strong evidence that dark matter behaves differently from normal matter. Observations of merging systems indicate that much of the cluster mass passes through with little direct interaction except gravity. While the hot gas is slowed and heated by impact, the galaxies inside clusters also feel the effect of this dense environment. A spiral galaxy moving through the hot intracluster gas can lose some of its own gas through pressure, a process known as ram pressure stripping. In simple terms, the galaxy pushes through the thin but extensive cluster medium, and some of its gas is swept away. Since gas is the raw material for future star formation, this process can reduce the birth of new stars. Frequent gravitational encounters, though often not direct collisions, can also disturb galactic shapes and alter orbits. Over time, dense cluster environments tend to contain many elliptical and lenticular galaxies, while rich gas-bearing spirals are often more common in less crowded regions. Environment does not determine every detail, but it strongly influences galactic evolution within clusters. At the center of many clusters lies giant elliptical galaxy, often far larger and brighter than most of its neighbors. These central galaxies may grow through repeated mergers and by collecting stars stripped from smaller systems. Around them, a faint glow of intracluster light can spread through the cluster. This light comes from stars that are not tightly bound to any single galaxy, but move within the cluster as a whole. Their presence shows that the cluster is not merely a collection of separate islands. Matter can be redistributed from galaxy to galaxy and into the shared cluster environment. Even the stars themselves can become part of the broader gravitational system. The scale of a galaxy cluster is difficult to hold in ordinary thought. Distances between galaxies within a cluster are often measured in millions of light years. The total mass can equal that of hundreds of trillions of suns. The hot gas can extend across regions so broad that light takes millions of years to cross them. Yet despite this size, a cluster remains a local object compared with a full cosmic web. It is one bound knot within the larger arrangement of filaments and superclusters. This contrast is essential to the sense of scale. What seems unimaginably large at one level becomes a single unit at the next. Galaxy clusters also serve as laboratories for cosmology. Their abundance at different distances, their internal temperatures, their mass distributions, and their merger histories help test models of structure formation. Because they sit at the high mass end of cosmic growth, they are sensitive to the rate at which matter gathers over time. Observations indicate that cluster formation depends on both the amount of matter in the universe and the way cosmic expansion changes across history. It remains uncertain in some details how feedback from black holes, star formation, and turbulent gas motion affects every cluster measurement, but the broad role of clusters as tracers of cosmic evolution is well established. The calm appearance of a cluster image can hide the violence of its history. Beneath the smooth glow of hot gas and the steady points of galaxies lies a record of repeated infall, high-speed motion, gravitational stripping, and ancient mergers. Yet the system also carries a quiet order. Its galaxies orbit through a shared well of gravity. Its gas settles, heats, and radiates. Its dark matter shapes the overall structure without shining. In this region of the universe, scale is no longer expressed mainly through separation across emptiness, but through the depth of a gravitational basin vast enough to contain thousands of galaxies and a reservoir of hot matter spread between them. A galaxy cluster shows how the cosmos can become crowded without becoming small, and how one bound structure can already exceed almost every ordinary measure of immensity. Within the wider setting of galaxy clusters and supercluster flows, there are smaller gravitational families where a limited number of galaxies share a common motion through space. These are galaxy groups, and among them lies the local group, the immediate cosmic neighbourhood that contains the Milky Way. In this region, scale begins to shift from the immense crowds of clusters to a quieter arrangement of a few large galaxies and many smaller companions, all bound together by gravity across distances that still exceed any familiar measure, yet feel more contained than the vast cluster environments beyond. The local group consists of more than 50 known galaxies, though new faint members continue to be identified as observations improve. Most of these are small dwarf galaxies, systems that contain far fewer stars than large spirals or ellipticals. The dominant members are two large spiral galaxies, the Milky Way and Andromeda, along with a somewhat smaller spiral called Triangulum. These major galaxies hold most of the mass in stars and gas within the group, while the numerous dwarf galaxies orbit them or move within the shared gravitational field. The entire system spans roughly 10 million light-years, a distance that light takes 10 million years to cross, placing every part of the local group in a relationship of slow gravitational influence. The motion of galaxies within this group reveals that it is a bound system. While the broader universe expands on large scales, the local group has enough internal gravity to resist that expansion within its own boundaries. The Milky Way and Andromeda are moving toward one another, not apart. Their mutual attraction dominates over the general expansion at this scale. Observations indicate that these two galaxies will approach, interact, and eventually merge over billions of years. This long future event unfolds slowly, with no sudden collapse, but it reflects the underlying fact that within a group, gravity can overcome cosmic expansion. Dwarf galaxies within the local group show a wide range of properties. Some contain active star formation, with gas clouds that continue to collapse into new stars. Others are more quiescent, with little remaining gas and older stellar populations. Many of these smaller galaxies orbit larger hosts, forming systems of satellites. The Milky Way itself has several known satellite galaxies, including the Large Magellanic Cloud and the Small Magellanic Cloud, which are visible from the southern hemisphere as faint glowing patches in the night sky. These satellite galaxies are not static companions. They move along orbits shaped by gravity, and over time their structures can be altered by tidal forces, which are differences in gravitational pull across their extent. Tidal interactions are a key process within galaxy groups. When a smaller galaxy passes close to a larger one, the difference in gravitational force between its near side and far side can stretch and distort it. Streams of stars may be pulled away, forming faint trails that extend across space. Observations of the Milky Way reveal such stellar streams, remnants of past interactions and mergers with smaller galaxies. These features show that even within a relatively quiet group, galaxies are not isolated. They influence one another, exchange material, and sometimes merge to form larger systems. The local group carries a history of these gradual processes, written in the motions and structures of its members. Between the galaxies of the local group lies intergalactic space, which is not entirely empty. It contains very thin gas, traces of dark matter, and background radiation. The density of matter here is far lower than within galaxies or clusters, yet it still participates in the overall gravitational field. The presence of dark matter is especially important, although it cannot be seen directly. Measurements of galaxy motions indicate that the visible mass alone is not sufficient to bind the group. A larger halo of dark matter surrounds the system, extending beyond the visible edges of individual galaxies and providing additional gravitational cohesion. The scale of the local group allows certain measurements that are difficult at greater distances. Distances to nearby galaxies can be determined with relatively high precision using standard candles. which are objects of known brightness such as certain types of variable stars or supernovae. These measurements help calibrate the cosmic distance scale, providing a foundation for estimating distances to more remote galaxies in this way. The local group serves as a reference region for broader cosmological studies. Its relative proximity makes it a natural laboratory for understanding galaxy structure, motion, and evolution. Despite its modest size compared with clusters, the local group still stretches across distances that defy ordinary intuition. The separation between the Milky Way and Andromeda is about 2.5 million light-years. Light leaving Andromeda takes that long to reach the Milky Way, meaning that observations of it show the galaxy as it was 2.5 million years ago. Even within this smaller region, the connection between distance and time remains present. The group is a collection of systems seen not in a single moment, but across slightly different moments in cosmic history. The gravitational relationship between the Milky Way and Andromeda shapes much of the local group's dynamics. These two galaxies orbit a common center of mass, though their mutual attraction is drawing them closer over time. The smaller Triangulum galaxy also participates in this motion, influenced by the gravitational pull of its larger neighbors. Around each major galaxy, swarms of dwarf companions follow more complex paths, some bound tightly, others moving on more extended trajectories. The combined motion of all these members creates a dynamic system that evolves slowly over billions of years. Observations indicate that the local group is part of a larger flow of galaxies within a broader supercluster environment. Yet within its own scale it behaves as a coherent unit. The internal motions of its members are governed more by local gravity than by the expansion of space. This distinction marks an important transition in scale. Beyond this region, cosmic expansion dominates the relative motion of distant galaxies. Within it, gravity shapes the structure and future of the system in a more direct way. The local group does not contain the extreme conditions found in massive clusters, such as vast reservoirs of very hot X-ray emitting gas or thousands of galaxies in close proximity. Instead, it offers a quieter environment where interactions are less frequent but still significant over long times. Galaxies here retain more of their gas, allowing ongoing star formation in many cases. The contrast between this region and denser cluster environments shows how scale and density influence the behavior of galaxies. In this region, the sense of the universe changes from an abstract web and distant concentrations to a more personal neighborhood of galaxies that can be studied in detail. The Milky Way is no longer just one point among countless others. It is part of a small family, bound together by gravity, moving through space as a unit. The distances remain immense, measured in millions of light-years. Yet the structure feels more intimate than the vast, sparse architecture beyond. The local group represents a middle ground in cosmic scale, where the grand patterns of the universe begin to resolve into specific systems, each with its own history, motion, and internal complexity. Within the local group, the Milky Way emerges as a single galaxy with a structure that extends across a vast but more defined region of space. It is a barred spiral galaxy, meaning that its stars and gas are arranged in a flat rotating disk with spiral arms, while a central bar of stars stretches across its core. Surrounding this disk lies a more diffuse halo of stars and dark matter. In this region, attention settles on the broad body of one galaxy, where the scale of the universe becomes organized into a rotating system that contains hundreds of billions of stars and a wide distribution of gas and dust. The disk of the Milky Way spans about 100,000 light-years in diameter. Its thickness is much smaller by comparison, only a few thousand light-years from top to bottom in most regions. This gives the galaxy a flattened shape. similar in proportion to a thin disk rather than a sphere. Within this disk, stars orbit the galactic center along paths influenced by gravity. These orbits are not perfectly circular, and over long periods they can shift. But the general motion follows a rotation around the center. The Sun itself is located within this disk, about 26,000 light-years from the center, moving along with billions of other stars. The rotation of the galaxy reveals important information about its mass. Measurements show that stars farther from the center move at speeds that do not decrease as expected if only visible matter were present. Instead, their speeds remain relatively constant across large distances from the center. This observation indicates the presence of additional mass that does not emit light. This unseen component is attributed to dark matter, which forms an extended halo around the galaxy. The halo reaches far beyond the visible disk and provides much of the gravitational pull that holds the system together. Within the disk, matter is not evenly distributed. Regions of higher density form spiral arms, which appear as sweeping structures winding outward from the central bar. These arms are not fixed objects in the sense of solid features. They are patterns of higher density that move through the disk as waves. As gas and stars pass through these regions, the increased density can trigger the formation of new stars. Bright, young stars illuminate the arms, making them stand out in images of spiral galaxies. Between the arms, the density is lower, and older stars are more common. Gas and dust play a major role in the structure of the disk. Interstellar gas consists mainly of hydrogen, along with smaller amounts of other elements. Dust grains, made of heavier elements, are mixed within this gas. Although dust makes up only a small fraction of the total mass, it has a strong effect on light. It can absorb and scatter visible light, creating dark lanes that obscure parts of the galaxy when viewed from within, at longer wavelengths, such as infrared. This dust becomes more transparent, allowing deeper views into the structure of the Milky Way. The disk contains both young and old stars. Younger stars tend to be found near the spiral arms, where gas is abundant and star formation is active. Older stars are more widely distributed and can be found throughout the disk. The combination of different stellar ages reflects the ongoing process of star formation and evolution within the galaxy. Stars are born from collapsing clouds of gas, live for varying lengths of time depending on their mass, and eventually return material to the interstellar medium through stellar winds or explosive events. This recycled material contributes to future generations of stars. At the center of the Milky Way lies a dense region known as the galactic bulge. This bulge is a roughly spheroidal concentration of stars surrounding the central bar. It contains many older stars and shows a higher density than the outer disk. Observations indicate that at the very center of the galaxy resides a supermassive black hole, an object with a mass of millions of suns. This black hole exerts a strong gravitational influence on nearby stars, causing them to move at high speeds in tight orbits. Despite its mass, the black hole occupies a very small region compared with the overall size of the galaxy. Surrounding the disk and bulge is the galactic halo. This halo contains older stars, globular clusters, and a large amount of dark matter. Globular clusters are dense groups of stars that orbit the galaxy in extended paths, often far above or below the disk. These clusters are among the oldest known stellar systems, providing clues about the early history of the Milky Way. The halo itself is faint in visible light but significant in mass due to its dark matter content. It extends far beyond the visible boundaries of the disk, blending into the surrounding intergalactic environment. The Milky Way is not an isolated system. It interacts with nearby galaxies, especially its satellite companions. The Large Magellanic Cloud and the Small Magellanic Cloud are the most prominent of these satellites. They orbit the Milky Way and are connected to it by streams of gas and stars, evidence of past interactions. Over time, smaller galaxies can be drawn into the Milky Way and merge with it, adding their stars and gas to the larger system. This process of hierarchical growth, where larger structures form through the merging of smaller ones, is a key feature of galaxy evolution. The scale of the Milky Way remains immense when compared with familiar distances. Light takes 100,000 years to travel from one side of the disk to the other. Even the distance between nearby stars is measured in light years, far beyond the scale of planetary systems. Yet within the context of the larger universe, the Milky Way is one galaxy among many, a single member of the local group and a small part of the cosmic web. In this region, the sense of scale becomes more structured and tangible. The galaxy is not a scattered collection of distant points, but a coherent system with rotation, layers, and internal processes, stars, gas, dust, and dark matter all contribute to its form. The Milky Way shows how the vastness of the universe can be organized into a single, connected system, where motion, gravity, and time shape a disk of light and matter that spans 100,000 light years, yet remains only a small part of the larger cosmos. Within the broad disk of the Milky Way, the spiral arms and the clouds within them form a more detailed inner region, where the galaxy's visible character becomes clearer. These arms are not rigid structures made of the same stars forever holding the same shape. They are regions of enhanced density that move through the galactic disk, influencing the motion of gas and stars as they pass. In this region, the scale of the universe is carried not by the full width of the galaxy alone, but by the long luminous lanes where gas gathers, dust thickens, and new stars begin to appear. The Milky Way is difficult to map from within because the solar system lies inside the disk rather than above it. Dust blocks much of the visible light across long lines of sight, and the galaxy must be reconstructed through many different kinds of observation, including radio, infrared, and stellar motion studies. Even so, observations indicate that the Milky Way contains several major spiral arms, along with smaller arm segments and spurs. A spur is a shorter branch-like structure between larger arms. The Sun appears to lie in one such smaller feature, often called the Orion spur or Orion arm, between larger neighbouring arms. This local position provides a useful point of view, though not a central one. Spiral arms stand out because gas is compressed as it moves through these denser regions. When large clouds of gas are squeezed, parts of them can become unstable and begin to collapse under their own gravity. This process leads to star formation. For that reason, the arms contain many young, bright stars, especially massive blue stars that shine intensely but live for relatively short times. Because these stars do not live long enough to drift far from their birthplaces, they mark out the arms clearly. Their light gives spiral galaxies much of their visible pattern. The arms are therefore not simply collections of stars. They're active regions where gas, dust, and gravity work together to create new stellar populations. The gas within the arms exists in several forms. Some of it is cold and neutral, meaning the hydrogen atoms remain intact and do not carry electric charge. Some of it is warmer and more diffuse. Some is molecular, meaning atoms join into molecules, especially molecular hydrogen, though this is often traced indirectly through other molecules such as carbon monoxide. Molecular clouds are among the coldest and densest regions in the interstellar medium. The interstellar medium is the matter that fills the space between stars, made mostly of gas with a small fraction of dust. Within the spiral arms, molecular clouds can grow to immense sizes, spanning dozens or even hundreds of light years and containing enough material to form many thousands of stars. Dust clouds thread through these regions as dark lanes. The dust itself consists of tiny solid grains made of heavier elements such as carbon, silicon, oxygen, and iron, often combined into minerals or carbon-rich particles. These grains are extremely small, but when spread through large clouds they can absorb and scatter visible light very effectively. As a result, some star-forming regions are hidden behind curtains of dust when viewed in ordinary light. Infrared observations can penetrate much of this obscuration, revealing stars still embedded in their natal clouds. Radio observations can trace the cold gas itself. In this way, the spiral arms appear very different depending on the wavelength used to observe them. Within the densest parts of molecular clouds, gravity slowly overcomes internal pressure and turbulence in localized pockets. These pockets contract and fragment, producing clusters of forming stars. A forming star begins as a collapsing concentration of gas and dust, heating as material falls inward. Around many young stars, disks of leftover material remain, and within some of these disks planets may later form. In the largest star-forming complexes, dozens or hundreds of young stars emerge within the same general cloud. Some are small and cool, others are massive and bright, releasing strong ultraviolet radiation and powerful stellar winds that reshape the surrounding gas. These newly formed stars can carve cavities, ionize nearby hydrogen, and create glowing nebulae, which are clouds of gas made visible by energetic radiation. The arms are therefore regions of both creation and disruption. Star formation begins within dense clouds, but the stars that emerge can quickly alter or disperse the material around them. Massive stars live short lives and may end in supernova explosions, scattering heavy elements back into the interstellar medium. These explosions send shock waves through nearby gas, sometimes compressing new regions and sometimes tearing clouds apart, over long spans of time. The arms are renewed by a balance of inflow, compression, starbirth, radiation, and stellar death. They are not calm lanes in a fixed galactic design. They are shifting environments in which matter circulates and changes state. Not every part of a spiral arm forms stars at the same rate. Conditions vary from one cloud to another depending on density, temperature, magnetic fields, turbulence, and local history. Observations indicate that some giant molecular clouds remain relatively quiet for long periods before becoming active, while others host major bursts of star formation. It remains uncertain in full detail which local factors dominate at every stage, because star formation is shaped by many interacting processes. What is clear is that the spiral arms provide favorable large-scale conditions by gathering and compressing gas. Within those conditions, smaller physical processes determine which clouds collapse and which remain stable for longer. The scale of these arm regions remains immense, even though attention has moved inward from the full galactic disk. A single giant molecular cloud may span a distance far greater than the separation between the Sun and the nearest stars. A star-forming complex can contain enough material to make thousands of suns. The luminous arc of one spiral arm extends across tens of thousands of light years. Yet these same structures are only parts of one galaxy, itself one member of a small group, itself one element within much larger cosmic architecture. The movement inward does not erase immensity, it changes its form. From within the Milky Way, the night sky along the galactic plane appears crowded because the line of sight runs through the disk and across parts of these arm structures. Dense star fields, dark dust lanes, glowing nebulae, and distant clusters all overlap in projection. What seems at first like a continuous band is in fact a layered view through different regions of gas, dust, and stars at different distances. The spiral structure is not directly visible as an external shape from Earth, but it reveals itself through this complexity and through careful mapping across many wavelengths. In this region, the galaxy becomes a place of texture rather than outline. The broad disk resolves into lanes, clouds, and star-forming environments. Dust dims and reddens the light of distant stars. Gas gathers into cold reservoirs. Dense knots collapse into new suns. Radiation and shock waves reshape the surrounding medium. The real scale of the universe here is measured in the size of structures large enough to build stellar populations and in processes slow enough to unfold across millions of years, yet local enough that one arm of one galaxy can contain a whole landscape of birth, change, and luminous matter suspended in the dark. Within the spiral structure of the Milky Way, there is a more local region where the scale of the galaxy becomes easier to feel through the spacing of individual stars. This is the stellar neighborhood around the Sun, a small part of the Orion Spur where nearby stars, gas clouds, and faint interstellar material occupy a volume that is modest by galactic standards, but still vast beyond ordinary experience. In this region, the universe no longer appears mainly as arms and giant clouds stretching across thousands of light years. It appears as a scattered population of stars separated by dark intervals so large that even the nearest neighbours lie at distances measured in years of light travel. The Sun is one ordinary star among many in this neighbourhood. It is not unusually large, unusually bright, or placed in any distinguished location within the galaxy. It belongs to the general stellar population of the Milky Way disk, orbiting the galactic centre with countless other stars. Around the Sun. The local distribution of stars is thin enough that the night sky between them is mostly empty, yet dense enough that many stars lie within a few dozen light years. A light year is the distance light travels in 1 year, and even this unit, which seems natural in astronomy, represents a span so great that no spacecraft built by humans has come close to crossing it in practical time. The nearest known star system to the Sun is Alpha Centauri, a multiple star system about 4.3 light-years away. This means that the light seen from it tonight leaves that system more than 4 years ago. Several other stars lie within 10 light-years, and many more within a few dozen. Even so, the spacing remains immense. If the Sun were reduced in thought to a grain on a wide plane, the next grains would not cluster beside it, but would lie many kilometers away in proportion. The local neighborhood is therefore not crowded in the ordinary sense. It is spacious, quiet, and dominated by separation. Nearby stars vary widely in mass, temperature, brightness, and age. Many of the closest are red dwarfs, which are small, cool, and faint stars far more numerous than stars like the Sun. Because they shine weakly, they are difficult to see over great distances, even though they make up a large share of the stellar population. Larger and hotter stars exist as well, but they are less common. White dwarfs, the dense remnants of stars that have exhausted their nuclear fuel, are also present in the local region. Each nearby star carries its own history of formation and evolution, yet together they reveal the ordinary character of the Milky Way's disk population. The neighborhood around the Sun also contains interstellar gas and dust, though at much lower density than the giant molecular clouds found in active spiral arm regions. The solar system is currently moving through an area known as the local interstellar cloud, a thin region of warm gas embedded within a larger cavity called the local bubble. The local bubble is a region of relatively low-density hot gas that may have been shaped by ancient supernova explosions. Observations indicate that the local interstellar medium is not uniform. It contains variations in temperature, density, magnetic field strength, and chemical composition across distances of many light years. Even in a relatively quiet stellar neighborhood, space between stars is not truly empty. This local environment matters because it shapes the outer boundary of the solar system, the solar wind, a flow of charged particles from the Sun, pushes outward until it meets the surrounding interstellar medium. That interaction defines a broad boundary region far beyond the planets. The nearby stars do not strongly affect the solar system in daily terms, but the larger galactic environment provides the background conditions through which the Sun moves, over long times. The solar system passes through different regions of the galaxy, encountering changing interstellar surroundings. These changes occur slowly and over spans far beyond human history. The stellar neighborhood also reveals how motion shapes the galaxy on local scales. Stars do not sit fixed in a permanent arrangement. Each one follows its own orbit around the galactic center, while also moving with its own local velocity relative to neighboring stars. Because of this, the patterns seen in the sky change over time. Constellations appear stable only because human lifetimes are short, compared with the timescales of stellar motion, over tens of thousands of years. The familiar figures drawn between stars gradually distort. Over millions of years, the local sky becomes entirely different. The nearby stellar neighborhood is therefore not a frozen scene but a slow current of individual suns passing through the disk. Among the stars of this region are open clusters and moving groups, which are loose associations of stars that form together and retain some shared motion for a time. Open clusters are collections of stars born from the same cloud, often still relatively young and found within the galactic disk. Over long periods, gravitational interactions tend to disperse them, adding their stars to the general background population. The Sun may once have belonged to such a cluster in the distant past, though its original siblings are now difficult to identify with certainty. This possibility reflects a broader truth of the local neighborhood. Many stars now seen as isolated likely begin in groups before spreading through the galaxy. The local scale also makes the search for planets more direct. Many nearby stars are now known to host planets, including rocky worlds and gas giants. Observations indicate that planets are common in the galaxy, and the stellar neighborhood provides many of the best studied examples because nearby systems are easier to observe in detail. Some planets orbit close to small red dwarfs, others circle stars more like the Sun. It remains uncertain how many nearby worlds may possess conditions suitable for surface liquid water over long periods, but the local region shows that planetary systems are not rare exceptions. They appear to be a common outcome of star formation. At this distant scale, the Milky Way becomes more personal without becoming small. The Sun's neighborhood is only a tiny fraction of the galaxy, yet it contains a broad range of stars, interstellar matter, stellar remnants, and planetary systems. Distances of a few light years separate one stellar system from the next. Tens of light years encompass dozens of known stars. Hundreds of light years bring entire local patterns of clouds and clusters into view. The density is low compared with the packed star fields toward the galactic center, but the region remains rich enough to reveal the basic architecture of stellar life in the disk. In this region, the real scale of the universe is carried by emptiness between stars. It is not the emptiness of cosmic voids, which stretch across millions of light years, but a more intimate kind of emptiness, where even the nearest sun beyond the solar system remains unimaginably far away. The stellar neighborhood shows that a galaxy is not a continuous blaze of closely packed light. It is a spacious system in which stars are scattered through darkness, each surrounded by its own local environment, each moving through the thin medium between suns. Here the cosmos begins to narrow toward the solar system, yet the distances remain large enough that even the closest neighbouring stars stand apart like quiet islands in a very wide sea. Beyond the known planets and the main belt of icy bodies that orbit in the flattened plane of the solar system, there is a far more distant region where the sun's influence continues in a weaker, broader form. This outer frontier is commonly called the Oort cloud, a proposed vast reservoir of icy bodies surrounding the solar system at extreme distances. In this region, the scale of the universe narrows from the spacing of stars to the outermost reach of one star's gravitational domain. Yet the distances remain so large that the boundary between solar space and interstellar space becomes gradual rather than sharply drawn. The Oort cloud has not been observed directly as a complete structure. Its existence is inferred from the paths of long-period comets, which are comets that take many thousands or even millions of years to complete one orbit around the Sun. These comets arrive from all directions rather than mainly from the flat plane in which the planets orbit. That pattern suggests a roughly spherical source region rather than a disk. Observations indicate that many such comets begin their journey far beyond the known major planets, in a distant cloud of icy remnants left over from the early formation of the solar system and later redistributed by gravitational interactions. The idea of the Oort cloud describes not a solid shell but an immense, sparse swarm of objects orbiting the Sun at distances perhaps extending from a few thousand astronomical units to tens of thousands, and possibly more than 100,000 astronomical units. An astronomical unit is the average distance between Earth and the Sun. Written this way, the numbers already feel large, yet their meaning becomes clearer in light years. The outer portions of the cloud may extend to about 1 or even nearly 2 light years from the Sun, depending on how its boundary is defined. That means the Sun's long gravitational reach stretches a significant fraction of the way toward the nearest stars. The solar system, at this scale, is no longer just a compact family of planets. It becomes a diffuse sphere of icy debris embedded within the local stellar neighborhood. The objects of the Oort cloud are thought to be small icy bodies, likely made of water ice, carbon dioxide ice, methane, ammonia, rock, and other frozen materials. They are remnants of the early solar system, preserved in deep cold where sunlight is too faint to warm them significantly. In the young solar system, countless small bodies form alongside the planets. Some are incorporated into larger worlds, some collide and break apart, and some are scattered outward by the gravity of the giant planets. Over time, a fraction of these scattered bodies are sent into long, distant orbits, where they remain loosely bound to the Sun. The Oort cloud is thus understood as a fossil population, carrying evidence of ancient planetary rearrangement and gravitational scattering. Its structure may include an inner and outer region. The inner part, sometimes called the Hills cloud in some models, would be denser and more tightly bound, while the outer part would be more weakly held and more easily disturbed. The exact distribution remains uncertain because it depends on conditions in the early solar system. The migration history of the giant planets and the influence of passing stars and the galactic environment over billions of years. Observations indicate that long-period comets are consistent with such a distant source, but the number of objects, their total mass, and their detailed arrangement remain uncertain. The cloud is therefore a scientifically supported inference, rather than a directly mapped landscape. At these distances, the Sun still dominates gravity for bound objects, but its control is delicate. A passing star, even at a considerable distance, can perturb the orbits of Oort cloud bodies. The tidal effect of the Milky Way, meaning the weak but persistent gravitational influence of the galaxy across large distances, can also alter their paths over long times. These disturbances can nudge some icy bodies inward, sending them on elongated trajectories toward the inner solar system. When one of these bodies approaches the Sun, solar heating turns its surface ices into gas, forming the coma and tail that make a comet visible. In this way, a bright comet seen from Earth may begin as a dark, frozen object, resting for immense ages in the solar system's distant outer reservoir. The Oort cloud marks a profound change in scale within the solar system. The known planets, even the outer giants, orbit within a comparatively compact region. Neptune lies about 30 astronomical units from the Sun. The Kuiper belt extends farther, with many icy bodies beyond Neptune, but still mainly within a flattened disk. The Oort cloud lies vastly farther out and likely in all directions. This shift changes the geometry of the solar system from a predominantly flat system of major orbits to a more spherical and diffuse outer domain. The farther one moves from the Sun, the less the solar system resembles the simple diagram often shown in classrooms, and the more it resembles a fading gravitational presence surrounded by darkness. Sunlight in this region is extremely weak. At such distances, the Sun is no longer a brilliant dominating disk, but a very bright star among stars, though still brighter than the others. The energy received by an Oort cloud object is so small that its surface remains near the temperature of deep interstellar cold. Motion is also slow. Bodies in the outer cloud may take hundreds of thousands or millions of years to complete a single orbit. Their paths are so long and their movement so gradual that human history occupies only an instant by comparison. This slowness gives the region a quiet quality, as though time itself spreads thinner there. The cloud also represents the place where the solar system begins to overlap conceptually with its galactic setting. These objects orbit the Sun, yet they are vulnerable to the gravity of passing stars and the broader tidal field of the Milky Way. The boundary is not absolute. Some objects may be stripped away over time, others may be captured under rare conditions. In the early history of the Sun, when it likely forms within a denser stellar cluster, nearby stars may have played an important role in shaping the outer cloud. It remains uncertain how much of the present Oort cloud forms from the Sun's own scattered material alone, and whether some fraction may involve exchange or influence from neighbouring stellar systems during the earliest epoch of solar formation. Even though it is distant and largely invisible, the Oort cloud matters because it preserves memory. It holds material from the early solar system in cold storage and releases occasional messengers inward in the form of long-period comets. These comets carry primitive matter that has changed little since the time of planet formation. They also reveal that the Sun's domain extends much farther than the bright realm of planets. The ordinary idea of the solar system as a set of worlds circling close to the Sun captures only the inner part of its true extent. In this region, the real scale of the universe is expressed through weak attachment. The Sun still holds these distant icy bodies, but only gently. The cloud is vast, sparse, dark, and slow, suspended between the intimate order of the planetary system and the wider influence of the galaxy. Here one star's family fades outward into a nearly invisible sphere that may reach toward the nearest stars without touching them, a frontier where the solar system is still present, though only as a long gravitational whisper in the cold. Inside the distant sphere of the Oort cloud, the solar system becomes more concentrated again. The next region inward is the realm of the giant planets, a broad middle domain dominated by Jupiter, Saturn, Uranus, and Neptune. These worlds occupy a large range of orbital distance and contain most of the planetary mass in the solar system outside the Sun itself. In this region, scale is expressed through wide spacing, deep atmospheres, strong gravity, complex moon systems, and rings made of countless small particles. The giant planet realm is still far from the warmth and density of the inner solar system, yet it is much more structured than the sparse frontier beyond. The giant planets differ from the rocky worlds closer to the Sun. Jupiter and Saturn are gas giants, composed mostly of hydrogen and helium, with no solid surface in the ordinary sense. Uranus and Neptune are often called ice giants because, although they also contain hydrogen and helium, a larger fraction of their interiors consists of substances such as water, ammonia, and methane in dense, hot forms. These names describe composition rather than coldness alone. All 4 giant planets are large compared with Earth, but they are not enlarged versions of rocky planets. Their masses, densities, internal pressures, and atmospheric structures place them in a different category of world. Jupiter, the largest planet, dominates the giant planet region by mass. It contains more mass than all the other planets combined. Its gravity strongly influences the architecture of the solar system, affecting asteroid orbits, comet paths, and the distribution of smaller bodies. Jupiter lies about 5 astronomical units from the Sun, far beyond the orbit of Mars, yet still in the inner portion of the giant planet realm compared with the more distant outer worlds. Its visible atmosphere is marked by cloud bands, storms, and long-lived vortices, including the Great Red Spot, a persistent anticyclonic storm larger than Earth. Beneath the cloud tops, pressure rises steadily. Deeper down, hydrogen is compressed into unusual states, including metallic hydrogen, in which it conducts electricity. Saturn lies farther out, at about 10 astronomical units from the Sun, and is known most clearly for its extensive ring system. Although all the giant planets have rings, Saturn's are the brightest and most elaborate. These rings are made mostly of water ice particles ranging in size from tiny grains to large chunks. They orbit in a thin plane around the planet, forming bands, gaps, and waves shaped by gravity. Small moons embedded within or near the rings help maintain some of these structures. Saturn itself, like Jupiter, is composed mainly of hydrogen and helium and lacks a solid surface. Its average density is lower than that of water, though under actual planetary conditions this fact does not imply any practical floating comparison. It simply reflects the low density of its outer layers compared with rocky worlds. Farther still lie Uranus and Neptune, much colder and dimmer in sunlight. Uranus orbits at about 19 astronomical units from the Sun, and Neptune at about 30. Uranus is unusual because its rotation axis is tilted by about 98 degrees relative to its orbit, so it effectively spins on its side. This extreme tilt gives it unusual seasons lasting many years. Neptune, though slightly smaller than Uranus in diameter, is more massive and denser. Its atmosphere contains methane, which absorbs red light and contributes to its blue appearance. Despite receiving far less solar energy than the inner planets, Neptune shows active weather, including strong winds and transient storms. This internal activity indicates that planetary atmospheres can remain dynamic, even in the remote outer solar system. The spacing between these giant planets is itself a lesson in scale. The distance from Jupiter to Saturn is greater than the distance from the Sun to Jupiter. The gap from Saturn to Uranus is larger still, and the distance from Uranus to Neptune adds another broad span of darkness. In simple diagrams, planets often appear lined neatly beside one another, but the real solar system is mostly empty space. Even within this planetary region, the intervals between major worlds are immense. A spacecraft crossing these distances requires years of travel. Light from the Sun, which reaches Earth in about 8 minutes, takes hours to reach Neptune. Each giant planet also governs a system of moons, some of which are planetary worlds in their own right by size and complexity. Jupiter has dozens of known moons, including the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto. Ganymede is larger than the planet Mercury. Europa likely contains a subsurface ocean beneath its icy crust. Io is the most volcanically active body known in the solar system. Heated by tidal forces generated through interaction with Jupiter and neighbouring moons. Saturn's moons include Titan, which has a thick nitrogen atmosphere and lakes of liquid methane and ethane at its surface, and Enceladus, which vents water-rich plumes from beneath an icy crust, indicating a subsurface ocean. Uranus and Neptune also possess rich moon systems, though they're less well studied because of their great distance. Triton, Neptune's largest moon, is especially notable for its retrograde orbit and likely capture from the Kuiper belt. These moon systems show that the giant planet realm is not composed merely of 4 isolated large planets. Each giant world acts as the centre of a smaller planetary system, with moons, rings, magnetic fields, and environments shaped by gravity and radiation. Around Jupiter especially, strong magnetic forces trap charged particles and create intense radiation belts. Similar, though different magnetospheres surround the other giant planets as well. These invisible fields extend far into space and interact with the solar wind, producing auroras and complex plasma environments. A magnetosphere is the region around a planet where its magnetic field dominates the motion of charged particles. In the giant planet realm, these magnetic domains add another layer of scale, surrounding the planets far beyond their visible atmospheres. The giant planets also preserve information about solar system formation. Because Jupiter and Saturn contain large amounts of hydrogen and helium, they reflect conditions in the early protoplanetary disk when these light gases are still abundant. Uranus and Neptune suggest a different formation pathway or growth history, perhaps involving slower accumulation or outward and inward migration during the early rearrangement of planets. Observations of exoplanet systems show that giant planets can move significantly from their birthplaces, and models of the early solar system indicate that migration of the giant planets likely shapes the distribution of smaller bodies. It remains uncertain in detail exactly how far each planet migrates and in what sequence every early orbital change occurs, but their present arrangement carries the outcome of those ancient movements. The light and heat in this region are weak compared with the inner solar system. Sunlight at Jupiter is already much fainter than at Earth. By Neptune, it is only a small fraction of that level. Temperatures are low in the upper atmospheres and on the surfaces of icy moons, yet internal heat remains important. Jupiter, Saturn, and Neptune radiate more energy than they receive from the Sun, showing that planetary interiors still release stored heat. This inward source helps drive atmospheric motion and maintains dynamic conditions despite great distance from the Sun. In this region, the real scale of the universe takes the form of broad orbital architecture. 4 giant planets spread across billions of kilometers of space, each surrounded by its own family of moons and rings, each shaping nearby matter through gravity, radiation, and motion. The solar system here appears spacious, layered, and cold, yet still richly active. What seems from afar like a simple set of outer planets becomes, on closer attention, a wide middle kingdom of deep atmospheres. Icy satellites, and vast gaps of darkness between worlds. Inside the broad realm of the giant planets, the solar system changes in character. Distances between worlds become shorter, sunlight grows stronger, and the dominant planets are no longer deep atmospheres of hydrogen and helium, but smaller, denser bodies made largely of rock and metal. This is the inner planet region, where Mercury, Venus, Earth, and Mars orbit the Sun within a relatively compact span. In this region, scale is expressed through contrast. These planets are tiny compared with the giant worlds beyond, yet they are the sites where solid surfaces, mineral crusts, volcanic plains, mountains, valleys, and atmospheres of varying thickness come into view. The solar system becomes warmer, brighter, and more concentrated, though it remains vast enough that even these closer planetary orbits are separated by immense distances. Mercury lies nearest to the Sun, at an average distance of about 58 million kilometers. It is the smallest of the four inner planets, and the one most directly exposed to the Sun's radiation, with only a very thin exosphere, meaning a sparse envelope of particles rather than a true substantial atmosphere. Mercury cannot retain heat well from one side of the planet to the other. As a result, its surface experiences extreme temperature differences between day and night. The planet's crust is heavily cratered, preserving a record of ancient impacts. Large basins and long cliffs indicate that Mercury cools and contracts over time, causing its surface to wrinkle as the interior slowly loses heat. In composition, it has an unusually large metallic core relative to its size, making it denser than most bodies of similar scale in the solar system. Farther out lies Venus, similar to Earth in size but very different in condition. Venus is wrapped in a thick atmosphere composed mainly of carbon dioxide, with clouds of sulfuric acid high above its surface. This dense atmosphere produces an intense greenhouse effect, trapping heat so efficiently that the planet's surface becomes hotter than Mercury's despite being farther from the Sun. Pressure at the surface is crushing, and temperatures are high enough to melt lead, radar observations, which can penetrate the cloud cover that blocks visible light, reveal plains of volcanic rock, large shield volcanoes, deformed highlands, and relatively few impact craters compared with more ancient surfaces elsewhere. This suggests that much of the visible surface is geologically younger than the oldest terrains in the solar system, perhaps reshaped by widespread volcanism or other large-scale resurfacing processes. It remains uncertain exactly how Venus loses interior heat over long times, and whether its surface changes in episodic global events or through more continuous regional activity. But observations indicate that it is not a static world. Earth occupies the next orbit, about 150 million kilometers from the Sun on average. In this inner region, Earth stands out because liquid water persists stably at the surface under present conditions, and because its atmosphere, magnetic field, and active geology interact in a way that supports a long-lived biosphere. Yet in terms of cosmic scale, Earth remains a small rocky planet orbiting an ordinary star. Its diameter is only a little more than 12,000 kilometers, tiny compared with the size of the Sun and almost negligible against planetary orbits. What makes Earth significant scientifically is not its size but the combination of its conditions. Its atmosphere is mainly nitrogen and oxygen. Its surface is divided between ocean and land. Its crust moves through plate tectonics, slowly reshaping continents and seafloor over immense spans of time. Its magnetic field, generated by motion in the liquid outer core, helps deflect much of the charged solar wind. These features together make Earth a particular case within the inner planets rather than a typical one. Mars lies farther outward, at about 228 million kilometers from the Sun. It is smaller than Earth and has a much thinner atmosphere, also composed mainly of carbon dioxide. Today its surface is cold and dry, with polar ice caps, vast volcanic provinces, deep canyons, ancient river valleys, and mineral evidence that liquid water once existed far more extensively than it does now. Mars preserves a record of environmental change. Observations indicate that early Mars once had a thicker atmosphere and more persistent surface water, at least in some regions and periods. Over time it loses much of that atmosphere, partly because of its lower gravity and the weakening or loss of a global magnetic field early in its history. The result is a planet that still shows traces of a wetter past while existing now as a cold desert world shaped by dust, wind, seasonal frost, and ancient geological memory. Between Mars and the giant planets lies the main asteroid belt, a region filled with countless rocky and metallic bodies orbiting the Sun. Although often pictured as a crowded field, it is in reality mostly empty space, with objects separated by vast distances. The belt contains material that never forms into a planet, likely because Jupiter's gravitational influence stirs the region and disrupts large-scale accretion. Some asteroids preserve primitive solar system matter, while others are fragments of larger bodies that partially melt and differentiate early in solar history. This belt marks the outer boundary of the inner planet region in a compositional sense, though the 4 terrestrial planets remain its central members. These inner planets are often called terrestrial planets because they are made primarily of silicate rock and metal. Their structures differ from those of the giant planets in fundamental ways. Each has a dense core, a mantle of rocky material, and a crust at the surface, though the thickness, composition, and activity of these layers vary. Their smaller size compared with the giant planets means they cool differently over time. Internal heat, radioactive decay, mantle convection, impact history, and atmospheric loss all influence how each world evolves. The inner region therefore presents not one kind of planet repeated 4 times, but 4 distinct outcomes shaped by shared origin and diverging history. The spacing of the inner planets is much tighter than the spacing among the giant planets, yet it still dwarfs human scales. The distance from Earth to the Moon, which already seems enormous in human terms, is tiny compared with the distance from Earth to Mars or Venus. Spacecraft travel between these worlds in months, not because the distances are small, but because they are far smaller than those to the outer planets. Sunlight is also stronger here. Solar energy drives atmospheric motion on Venus, climate and weather on Earth, and seasonal change on Mars. Mercury, with almost no atmosphere, receives the Sun's radiation more directly at the surface. Across this region, increasing proximity to the Sun changes temperature, chemistry, and the stability of surface materials. The inner planets also reveal the importance of atmosphere. Mercury is nearly bare. Venus is wrapped in an atmosphere so thick that its surface is hidden and overheated. Earth's atmosphere is moderate in pressure and composition, allowing clouds, rain, and a hydrological cycle. Mars has only a thin remnant, enough for weather and dust storms but not enough to sustain stable liquid water widely at the surface today. These differences show how a planet's size, distance from the Sun, geological activity, and magnetic history can influence whether gases are retained, lost, or transformed. In this region, the real scale of the universe takes the form of small worlds widely spaced around one star, each carrying a separate environmental history within a compact but still immense zone of light and rock. The inner solar system is brighter and denser than the regions beyond, yet it does not feel crowded. Each orbit encloses a broad path through space. Each planet is separated from the next by long reaches of emptiness. Here, solid surfaces become important, geology comes forward, and the meaning of planetary scale becomes more familiar without losing its cosmic vastness. At the center of the inner planet region stands the Sun, the dominant source of light, heat, and gravity for the entire solar system. In this region, attention rests not on orbiting bodies, but on the star itself, a sphere of hot plasma containing almost all the mass in the solar system. Plasma is a state of matter in which electrons are no longer bound tightly to atomic nuclei, allowing charged particles to move freely. The Sun is made mostly of hydrogen, with a large amount of helium and smaller quantities of heavier elements. Its presence defines the scale of everything around it. The planet's orbit because of its gravity, their temperatures, atmospheres, and histories are shaped by its radiation. Even the distant outer regions remain part of its domain because the Sun's mass so thoroughly outweighs that of all other solar bodies combined. The Sun contains about 99.8% of the total mass of the solar system. This single fact explains much of its control. The giant planets may seem immense when considered alone, but beside the Sun they are minor companions. Jupiter, the largest planet, contains only a small fraction of the Sun's mass. The Sun's diameter is about 1.4 million kilometers, wide enough that more than 100 Earths could be lined across it. Its volume is vast enough to hold more than 1 million Earths. Though the densities of stars and planets differ greatly, and such comparisons are only rough ways to picture size, even so, the Sun is not an unusually large star by galactic standards. It is a main sequence star of medium mass, one among the many ordinary stars that fill the Milky Way. The Sun shines because of nuclear fusion in its core. Fusion is the process in which lighter atomic nuclei combine to form heavier nuclei, releasing energy. In the Sun's central region, pressure and temperature are so high that hydrogen nuclei can overcome their mutual electrical repulsion and fuse through a chain of reactions that ultimately produces helium. A small amount of mass is converted into energy in this process. According to the relation between mass and energy described by modern physics, that energy begins deep in the core and works outward over long timescales. The sunlight reaching Earth today is linked to energy generated in the Sun's interior, though the path from core to surface is complex and slow. The Sun is layered. At the center lies the core, where fusion occurs and temperatures reach about 15 million degrees Celsius. Surrounding the core is the radiative zone, where energy moves outward mainly through radiation. In this region, photons, meaning particles of light, are repeatedly absorbed and re-emitted by matter. Because this happens over and over again, the effective journey outward is extremely slow. A photon created in the deep interior does not travel straight to the surface. It follows an indirect path shaped by countless interactions. Beyond the radiative zone lies the convective zone, where energy is transported mainly by bulk motion of hot plasma rising and cooler plasma sinking. This churning motion creates the granulated appearance seen on the solar surface at fine scale. The visible surface of the Sun is called the photosphere. It is not a solid surface like the crust of a rocky planet, but the layer from which most sunlight escapes into space. Its temperature is about 5,500 degrees Celsius. Darker patches called sunspots sometimes appear there. These are regions of intense magnetic activity that are cooler than the surrounding photosphere and therefore look darker by contrast. Sunspots can persist for days or weeks, changing in number over the course of the solar cycle, an approximately 11-year pattern in solar magnetic activity. This cycle affects the frequency of eruptions, flares, and other magnetic events at the Sun. Above the photosphere lies the chromosphere and then the corona, the Sun's outer atmosphere. The corona extends far into space and is visible during total solar eclipses as a pale halo around the darkened Sun. One of the most striking features of solar physics is that the corona is far hotter than the visible surface, reaching temperatures of more than 1 million degrees Celsius. Observations show that magnetic processes play a crucial role in heating the corona, but the exact balance of mechanisms remains an active area of research. The Sun therefore contains not only settled knowledge, but also continuing questions. Its broad structure and source of energy are well understood, while some details of how magnetic energy is transferred and dissipated remain under study. The Sun does not simply emit light. It also releases a continuous flow of charged particles known as the solar wind. This wind streams outward through the solar system, carrying the Sun's magnetic field with it and shaping a vast bubble in interstellar space called the heliosphere. The solar wind interacts with planetary magnetospheres, atmospheres, and surfaces. At Earth, these interactions help produce auroras near the poles. At other planets, the effects differ depending on magnetic field strength and atmospheric composition. The Sun's influence is therefore not limited to illumination and gravitational hold. It is also a source of plasma and magnetic structure extending far beyond the orbit of the planets. Although the Sun appears steady from Earth, it is dynamic at every scale. Convection stirs its outer layers, magnetic fields twist and reconnect, prominences rise and arc above the surface, solar flares release bursts of radiation, coronal mass ejections hurl large clouds of magnetized plasma into space. These events vary with the solar cycle and with local magnetic conditions. Most pass with little visible effect from the perspective of daily life. Yet they remind astronomy that a star is not a fixed lamp. It is an active body governed by gravity, nuclear reactions, fluid motion, and electromagnetism. The Sun's long-term history is also part of its scale. It forms about 4.6 billion years ago from a collapsing cloud of gas and dust, alongside the disk from which the planets emerge. It now resides in the stable middle period of its life, fusing hydrogen in its core. This phase lasts for billions of years in total. Over time, the Sun slowly becomes brighter as conditions in the core change. Eventually it will exhaust the hydrogen in its center, expand into a red giant, and later shed its outer layers, leaving behind a white dwarf. These future stages are well supported by stellar evolution theory and by observations of similar stars at different ages. The Sun is therefore ordinary not only in size but in life cycle. Its gravity governs planetary motion with remarkable regularity. The planets orbit because they're constantly falling through curved space under solar gravity, while moving sideways fast enough to keep missing the Sun. Their orbital periods reflect their distances. Their climates and surface conditions depend strongly on the amount of solar energy they receive. Even the smallest icy body in the outer reaches belongs to the Sun system because of this central mass. In that sense, the Sun is not merely one object among others in the solar system. It is the organizing center around which the whole structure exists. In this region, the real scale of the universe is concentrated into one star that outweighs nearly everything else nearby and powers an entire planetary system through fusion. The Sun is enormous compared with Earth, yet modest compared with many stars in the galaxy. It is ordinary in type, extraordinary in local importance, and central to every inner process of the solar system. Here the movement inward reaches the luminous source itself, a sphere of hot plasma whose gravity, light, magnetism, and long steady life make the surrounding worlds possible. Within the Sun's broad field of gravity and light, one small planet comes into focus as a particular world in orbital context. Earth is the next inward region, not yet as a place of continents, oceans, and daily life, but as a planet defined first by its position beside the Sun and Moon. In this region, the scale of the universe narrows from stellar dimensions to the geometry of one planetary system at close range. Earth appears neither central nor large. It is a rocky sphere orbiting an ordinary star at a moderate distance, accompanied by a single large natural satellite. The meaning of scale here lies in proportion, motion and relation, the size of Earth compared with the Sun, the distance between Earth and the Moon, and the thin orbital path along which this planet moves through space. Earth orbits the Sun at an average distance of 1 astronomical unit, about 150 million kilometers. This distance is great enough that sunlight takes about 8 minutes to arrive, yet small enough on cosmic terms that Earth completes one orbit in a single year. That orbit is not a perfect circle, but a very slight ellipse. The difference between the nearest and farthest points is small compared with the overall size of the orbit. Seasonal change on Earth is caused mainly not by this changing distance, but by the tilt of Earth's rotation axis relative to its orbital plane. This tilt, about 23.5 degrees, causes different hemispheres to receive different amounts of sunlight over the course of a year. Even at this scale, the familiar rhythm of seasons depends on geometry more than on proximity. Earth itself is a sphere slightly flattened at the poles, because rotation causes the equatorial region to bulge outward a little. Its average diameter is a little more than 12,700 kilometers. That seems large in human terms, yet beside the Sun it is very small. More than 100 Earths could fit across the Sun's diameter. In mass, the contrast is even more striking. The Sun contains about 333,000 times as much mass as Earth. These comparisons show clearly that Earth does not dominate its own wider environment. It moves within a solar system overwhelmingly controlled by a central star. The Moon introduces a second important scale. Earth's natural satellite is large relative to the planet it orbits. Its diameter is about 1/4 of Earth's diameter, which is a much larger ratio than is typical for most planetary moons in the solar system. The average distance between Earth and the Moon is about 384,000 kilometers. Light takes a little more than 1 second to cross this distance. In diagrams, the Moon is often drawn close beside Earth, but at true scale it is far enough away that all the other planets in the solar system would not fit neatly into that gap at once, unless one is careful about which dimensions are being compared. The Earth-Moon system is therefore more spacious than casual images suggest. The Moon's gravity affects Earth continuously. The most familiar result is the tide, the slow rise and fall of ocean water caused mainly by the gravitational pull of the Moon, and, to a lesser extent, the Sun. Tidal force comes from the difference in gravity across Earth's diameter. The side nearer the Moon is pulled slightly more strongly than Earth's centre, while the far side is pulled slightly less strongly. This produces 2 tidal bulges, because Earth rotates through these bulges. Coastlines experience changing sea level through the day. Tides also affect the solid Earth on a smaller scale and gradually alter the rotation and orbit of the Earth-Moon system. Over long periods, Earth's rotation slows slightly, and the Moon recedes from Earth by a few centimeters each year. The Moon also stabilizes Earth's axial tilt over long timescales. Without such a relatively large satellite, the tilt of Earth's axis could vary more chaotically under gravitational influence from other planets. Observations and dynamical models indicate that the presence of the Moon helps keep Earth's obliquity, meaning axial tilt, within a comparatively moderate range over long periods. This stability influences climate patterns across geological time. It does not remove all climate variation, but it contributes to long-term regularity in the planetary system. In this sense, the Moon is not merely an ornament in Earth's sky. It is part of the deeper mechanical setting in which Earth evolves. The origin of the Moon is best explained by the giant impact model. According to this model, early in Earth's history, a Mars-sized body collides with the young Earth. Material from the outer parts of both bodies is ejected into orbit and later gathers to form the Moon. This explanation fits many observed features, including the Moon's relatively low iron content compared with Earth, and similarities in isotopic composition between lunar and terrestrial rocks. Some details of the collision and the exact sequence of post-impact evolution remain under study, but the broad model is widely supported. The Earth-Moon system therefore reflects an early violent event that later leads to a stable orbital partnership lasting billions of years. Earth's orbit also places it within the Sun's habitable zone, the region around a star where surface temperatures can allow liquid water under suitable atmospheric conditions. This concept is useful but limited. Habitability depends on more than distance from the star alone. Atmosphere, planetary mass, magnetic field, geologic activity, and chemical history all matter. Even so, Earth's position is important. It receives enough solar energy to maintain a temperate range when combined with its atmosphere, but not so much that water must inevitably boil away, as on Venus under present conditions. Mars, farther outward, lies near the outer part of the Sun's habitable zone in simple models, but its smaller size and thin atmosphere lead to very different surface conditions today. Earth's context is therefore orbital and planetary at once. Seen from space, Earth's motion is steady and continuous. It rotates once every about 24 hours, creating the cycle of day and night. At the same time, it orbits the Sun at an average speed of about 30 kilometers per second. The Moon orbits Earth while both together orbit the Sun. The solar system itself moves within the Milky Way. None of these motions is felt directly in ordinary experience because they are smooth and shared by everything nearby. Yet they are always present. Earth is not resting in the universe. It is moving through layered systems of motion from the scale of the Earth-Moon pair to the scale of the galaxy. From a wider perspective, Earth is one rocky planet among many known worlds. Thousands of exoplanets are now confirmed around other stars, and many more candidates are known. Some are larger than Earth, some smaller, some hotter, some colder, some orbiting close to dim red stars, others circling stars unlike the Sun. This growing knowledge places Earth in a broader planetary context. It is special in being the only known inhabited world, but it is not unique in being a planet of rocky composition orbiting within a stellar system. Its scientific importance comes from being both ordinary in category and extraordinary in known biology. In this region, the real scale of the universe is expressed through relation. Earth is small beside the Sun, yet large enough to hold an atmosphere, oceans, and long geological history. The Moon is far from Earth, yet bound closely enough to shape tides, rotation, and stability. Together they form a local system inside a broader solar one. Before turning to the surface itself, Earth appears here as a moving sphere in space, modest in size, precisely placed. and held in a web of gravitational relationships that define the immediate stage on which all human history unfolds. On the surface of Earth, planetary scale narrows into a thin outer layer where rock, water, air, and life meet. This region is small compared with the full size of the planet and vanishingly small compared with the solar system, yet it contains all known human experience. In this region, the real scale of the universe is expressed through thinness. Earth may be more than 12,000 kilometers across, but the part occupied by oceans, weather, soils, forests, rivers, ice sheets, and living creatures forms only a delicate skin at the boundary between the solid planet below and the space above. What appears vast in daily life is, from a planetary view, a narrow surface film. The solid outer part of Earth is divided into crust and uppermost mantle, together forming the lithosphere, the rigid outer shell broken into tectonic plates. These plates move slowly over the softer underlying mantle. Continents shift, ocean basins open and close, mountains rise, and seafloors are renewed over immense spans of time. Yet the crust itself is thin. Oceanic crust is commonly only several kilometers thick. Continental crust is thicker, often tens of kilometers, but still very slight compared with Earth's radius. Even the tallest mountains and deepest mines barely scratch the outer skin of the planet. Human ideas of height and depth remain surface measures. Water covers about 70% of Earth's surface. The oceans dominate the visible exterior of the planet, forming a connected global body with an average depth of only a few kilometers. In human terms, this seems profound, and in practical terms it is. In planetary terms, it is extremely shallow. If Earth were reduced in thought to the size of a smooth sphere held in the hand, the oceans would be thinner than a surface sheen. Even the deepest trenches are small irregularities relative to Earth's full diameter. Yet within this thin hydrosphere, heat is stored and moved, gases are exchanged with the atmosphere, nutrients circulate, and life occupies nearly every level from sunlit shallows to dark abyssal plains. Above the land and sea lies the atmosphere, another thin layer that seems boundless from the ground but is physically slight. Most of its mass is concentrated close to the surface. The lower atmosphere, the troposphere, contains the bulk of weather, clouds, and water vapor. Above it, the stratosphere includes the ozone layer, which absorbs much of the sun's harmful ultraviolet radiation. Higher layers extend farther upward, becoming progressively thinner until they merge into the near vacuum of space. In relation to Earth's size, the atmosphere is as delicate as a translucent coating. Its total mass is tiny compared with the planet beneath it, yet it regulates temperature, distributes moisture, enables breathing for complex animal life, and shields the surface from many environmental extremes. Life exists within an even thinner zone, the biosphere. This is not a separate physical shell with a visible border, but the sum of regions where life is present. Most complex life occupies a narrow band near the surface. Forest canopies, grasslands, wetlands, coral reefs, agricultural fields, and cities all sit within a shallow vertical range relative to the planet's full dimensions. Microbial life extends deeper underground and higher in the atmosphere, and marine life reaches into the dark ocean depths. But even when all known living zones are combined, the biosphere remains extremely thin in planetary proportion. The living world is a surface phenomenon. Human beings occupy only a small part of this biosphere directly. Settlements are concentrated on land, mostly at low elevations relative to sea level, within climatic conditions that support agriculture, water access, and stable infrastructure. The highest inhabited plateaus, the driest deserts, the polar margins, and the densest tropical forests all demonstrate human adaptability. Yet the habitable zone for large settled populations remains selective. Civilization does not spread evenly across the surface. It clusters around coasts, rivers, plains, and moderate climates. From orbit, city lights may suggest a densely occupied world, but much of Earth's surface remains sparsely inhabited or uninhabited by humans. The surface itself is dynamic. Plate tectonics slowly rearranges continents and ocean floors. Erosion wears down mountains. Rivers carry sediment from high ground to sea. Glaciers advance and retreat where climate allows. Volcanic eruptions bring material from below to the surface. Earthquakes reveal the movement of crustal plates. Wind shapes dunes and redistributes dust across continents and oceans. Biological activity alters soils, atmosphere, and chemistry. The surface layer is therefore not merely a boundary. It is a zone of constant exchange among rock, water, air, and life. Yet all of this activity unfolds in a narrow envelope compared with the great depth of the mantle below. Seen from a sufficient distance, Earth's surface appears continuous, but at closer scale it resolves into complex patterns. Continents carry mountains, plains, deserts, river systems, and vegetation belts. Oceans show currents, sea ice, storms, and biological productivity. Clouds form and dissolve in changing weather systems driven by solar heating, rotation, and the movement of air and water. Seasonal change alters snow cover, plant growth, and the position of sunlight across latitudes. None of these patterns is static. The surface is always in motion, though some changes unfold over hours, others over centuries, and others over millions of years. The thinness of this inhabited layer becomes clearer when set against the space above. Commercial aircraft fly within the lower atmosphere. High mountains rise only a small fraction of the distance to the edge of space as conventionally defined. Orbiting spacecraft travel above nearly all the atmospheric mass. From that vantage, the atmosphere appears as a faint blue line around the planet. This visual impression is scientifically truthful. The conditions that support surface water, weather, and breathing occupy a narrow margin. Earth's habitability depends on preserving this margin within a broader environment that is mostly rock below and vacuum above. Time also shapes the human surface. Agriculture, cities, roads, reservoirs, and industrial systems have transformed large portions of land and altered atmospheric composition, nutrient cycles, and ecosystems. These changes are recent on geological timescales but significant within the surface system. Observations show warming of the climate system, widespread biodiversity loss, glacier retreat, sea level rise, and extensive modification of landscapes through human activity. These are not changes to the whole planet in bulk. They're changes to the thin outer layer where climate, ecology, and civilization interact. The planet remains physically vast beneath them, but the surface conditions on which human life depends are sensitive. The scale of ordinary life can hide this thinness. A forest seems immense from the ground. An ocean crossing feels enormous. A mountain range appears enduring and absolute. Yet from a planetary view, all these belong to a narrow exterior film. The deepest roots of trees, the foundations of buildings, the height of storms, and the depth of fertile soils all remain close to the boundary line between Earth and space. Even human history, written across thousands of years, occupies only a brief instant on the changing face of this surface shell. In this region, The real scale of the universe is carried by fragility and proportion. Earth's surface holds oceans, weather, landscapes, ecosystems, and every known human life. Yet all of it occupies only a thin outer rind on a small planet orbiting an ordinary star. The familiar world is broad enough to contain continents and civilizations, but narrow enough that from a wider view it appears as a delicate habitable skin, luminous, shifting, and slight. Within the thin surface world of Earth, this scale of reality narrows one final time into the human body and then into the structure of matter itself. In this region, the universe is no longer measured in light years, planetary diameters, or orbital distances. It is measured in meters, centimeters, and then in dimensions so small that ordinary sight cannot reach them at all. Yet this inward movement does not leave the cosmos behind. The same physical laws that govern stars and galaxies also govern cells, molecules, atoms, and nuclei. The human body is made of material forged in ancient stars, arranged by chemistry on Earth, and organized by biology into a living form. The largest scale and the smallest accessible scale meet here in continuity rather than in contrast. A human body appears solid, bounded, and self-contained. It has weight, temperature, structure, and motion. It occupies a narrow range of size compared with the living world around it. Most adults are between about 1 and 2 meters in height. That scale feels natural because it matches the reach of limbs, the dimensions of buildings, and the distances crossed in daily life. Yet the body is not a single thing in the simple sense. It is a changing collection of systems, bones, muscles, blood, nerves, organs, water, salts, fats, proteins, and countless living cells working together. The body is both one organism and a society of parts. Cells are the basic living units of the body. A cell is a microscopic compartment enclosed by a membrane and filled with water, dissolved molecules, and specialized structures. Many cells are so small that they can be seen only with a microscope. They vary in form and function. Nerve cells may extend over long distances within the body. Blood cells move through vessels. Muscle cells contract. Skin cells form protective layers. The human body contains trillions of cells, though exact estimates vary depending on method and body size. These cells do not float randomly. They are arranged into tissues and organs, linked by chemical signals, electrical activity, circulation, and mechanical support. The body's apparent unity emerges from coordinated complexity at scales too small for direct sight. Within each cell, chemistry shapes life. Water is the main medium. Dissolved within it are ions, sugars, lipids, proteins, and nucleic acids. Proteins are long chains of smaller units called amino acids folded into particular shapes. Their shape helps determine their function. Some act as structural elements. Some carry signals. Some accelerate chemical reactions as enzymes. Deoxyribonucleic acid, or DNA, stores hereditary information in sequences of molecular units. This molecule is not alive by itself, but within cells it participates in the copying, regulation, and expression of biological form. At this level, life depends on arrangement. The same basic atoms can exist in rock, ocean, air, or flesh. What changes is the structure into which those atoms are assembled. Molecules are groups of atoms joined by chemical bonds. A bond is the result of how electrons are shared or distributed between atoms. Water is a simple molecule made of hydrogen and oxygen. Carbon dioxide contains carbon and oxygen. Proteins and DNA are much larger and more complex. The chemistry of life depends especially on carbon, because carbon atoms can form stable chains and branching structures with many other elements. This allows a wide range of molecular forms. The human body is therefore not made from unusual matter. It is made from common elements assembled into extraordinarily complex patterns under the conditions available on Earth. Atoms themselves are mostly empty space in a practical structural sense. Each atom has a tiny central nucleus surrounded by a cloud of electrons described by quantum physics. Electrons do not orbit the nucleus like planets around the Sun in the old simple picture. Their behavior is better described by probability and energy states. Even so, the comparison with the central mass and surrounding region can help at first approach, as long as it is not taken literally. The nucleus contains protons and neutrons. Protons carry positive electric charge. Neutrons have no net electric charge. Together they account for almost all of the atom's mass. Electrons are much lighter and determine much of the atom's chemical behavior. The size difference within the atom is striking. The nucleus is tiny compared with the extent of the electron cloud. If an atom were enlarged to the scale of a stadium, the nucleus would still be much smaller than a visible ball at the center, while the electrons would occupy a diffuse region around it according to quantum rules. This does not mean matter is unreal or insubstantial. The solidity of ordinary objects arises from electromagnetic interaction and the quantum behavior of electrons and atoms, which prevent matter from collapsing into itself under ordinary conditions. The body feels solid because its atoms resist compression and because forces act consistently at human scales. Inside the nucleus, the scale narrows again. Protons and neutrons are made of quarks bound together by gluons through the strong nuclear force. This is one of the fundamental interactions of nature, responsible for holding atomic nuclei together despite the electrical repulsion between positively charged protons. Atomic nuclei vary in size and stability depending on the number of protons and neutrons they contain. Hydrogen, the simplest element, usually has one proton alone. Carbon has 6 protons. Iron has 26. Heavier elements such as gold, iodine, and uranium contain many more. These nuclei form in different astrophysical settings. Hydrogen comes largely from the early universe. Many heavier elements are built in stars or in explosive events such as supernovae and neutron star mergers. The atoms in the human body therefore carry a cosmic history. The calcium in bone, the iron in blood, the oxygen in water, and the carbon in every cell originate in processes far older than Earth itself. This inward scale does not end with certainty at every step. Physics describes atoms and nuclei with extraordinary accuracy. Yet some deeper questions remain open, especially where quantum theory and gravity meet under extreme conditions not found in the body. Biology explains much of cellular function and molecular inheritance, yet the full complexity of living systems still exceeds complete prediction from first principles. What is known is already profound. A human body is composed of ordinary matter arranged through natural history into living complexity. It is not separate from the universe. It is one form the universe takes. At this final inward level, the meaning of scale becomes quiet. The body seems large to a cell and small to a planet. A cell seems vast to a molecule and crowded to a person. An atom contains a minute nucleus and an extended quantum structure. Matter continues inward beyond sight, yet remains part of one continuous physical reality. The largest web of galaxies and the smallest nucleus described here are not disconnected realms. They belong to the same cosmos, governed by the same fundamental laws, linked through time by the formation of elements, the birth of stars, the making of planets, and the chemistry of life. The real scale of the universe is not only that it is vast, it is that its vastness continues inward as well as outward, and that one human body, standing briefly on a thin planetary surface, contains within it the record of both directions. The widest horizon remains far beyond direct travel, and the smallest structures remain beyond ordinary sight. Yet both can be known in part through observation, measurement, and patient thought. Galaxies gather in filaments across expanding space. Stars form within dusty arms. Planets circle one modest sun. On one of those planets, a thin atmosphere rests above oceans and rock. Upon that surface, life arranges atoms into cells, tissues, and minds able to notice the structure that surrounds and composes them. The inward and outward journeys meet in that act of noticing. Scale changes the meaning of everything it touches. A continent becomes a surface feature, an ocean becomes a shallow film, a planet becomes a small companion of a star becomes one light among hundreds of billions in a galaxy becomes one node in a larger web. Then the movement reverses. A body becomes a collection of cells, a cell becomes a chamber of molecules, a molecule becomes a pattern of atoms, an atom becomes a nucleus held in a quantum cloud. At every level, reality remains structured, lawful, and more spacious than first appearances suggest. The calmest conclusion is also the simplest. The universe is not only large, it is layered. Its scale is not a single number, but a sequence of worlds nested within worlds, outward into distance and inward into matter. Human life occupies a narrow middle range between these extremes. It is small, brief, and local, yet made from ancient cosmic material and capable of understanding some fraction of the whole. In that quiet fact, there is enough perspective for rest.